In today's video, we're going to be talking about optimal start, and I'll be presenting this idea to you that we have had optimal start wrong for the last 20 years. So although the discussion is about optimal start, most of this video we're actually talking about peak demand management, because peak demand management is related to optimal start. And we don't think about it like that. We think a lot about optimal start. We never think about peak demand management. And I've had this idea in my head for more than 5 years that peak demand and peak demand management is a problem with optimal start. I remember this idea first came to my head quite a few years ago. A sustainability engineer called me up and said, like, hey Bryce, we've just exceeded the peak demand on our building, which means that we'll be paying an increased cost for the next 12 months in our electricity bill. And I was thinking he would say that this happened at 3 or 4 o'clock in the afternoon. That's what I thought he would say. And he said we had a peak demand event at 7 a.m. in the morning. And I was surprised to hear that. And then for years after that, I was always thinking in the back of my head, that building starting up, the chillers starting up and all the AHU starting up at the same time because of optimal start, that's what's actually causing this peak demand event. But I've never had to really do anything about it because I never had a project as a consultant where the customer said, look, Bryce, give us a fee proposal to investigate why we're hitting our peak demand and what we do about it in the BMS. I've never had a project to do this, so I've never actually gone deep into it and really sort of studied it. But I recently just finished recording the first 14 video lessons for the peak demand management course in the BMS membership. So although it wasn't a consulting project, I had to go deep for about 3 weeks into peak demand management to put together the course. So I had to get an electricity bill and learn how that works. I had to create a spreadsheet for the last 4 years of exactly what month, what day, what time 9 buildings were hitting their peak. What was happening? When was it happening? And it was super interesting. The more deeper I went into this, to understand it better, to present it as a course, I realized that there's a massive issue here. The first problem is that we're not thinking about peak demand management at all. We're not thinking about it at all. It's not on our radar. And the second thing is that our optimal start, which is working well to achieve comfortable temperatures at occupancy time, is actually probably causing peak demand events, which show up as money on the electricity bill. So let's get deeper into this. So let's just first start off with, what is the objective of optimal start, right? So 30 years ago when we had no optimal start, and just pausing for a second, there's a lot of countries in the world right now that don't have optimal start. So if you live in one of those countries where you don't have optimal start, or thinking through from 30 years ago, what we used to do was we used to say at 8:30 a.m. we want to have comfortable temperature in this commercial office at 8:30 a.m. There was no optimal start, so we just said let's just start the time schedule 2.5 hours earlier, and we started the building at 6 a.m. So we started at 6 a.m. and the building ran for 2 or 3 hours, and then by the time we got to occupancy time, it was nice and comfortable. It was nice and warm, or nice and cool, was comfortable. So that was what optimal start was. And just start the building up early. Doesn't matter. We don't care about electricity or building's energy efficiency ratings, and we'll just air condition the building beforehand. So that, and at some stage, people were thinking, well, hang on a second, that's not very smart, because maybe on the hottest day of the year or the coldest day of the year, we need to start, at 6 a.m. But for many other months of the year, in other seasons, when it's not very hot or not very cold, we don't need to start at 6 a.m. We can start at 7 a.m. or 7:30 or something like that. So originally, optimal start was purely a thing about, let's just pre-start the building so it's comfortable at 8:30 in the morning. And then it sort of shifted into energy efficiency, where it was let's try and start the building as late as possible to achieve comfortable temperatures of occupancy. So rather than running everything for 3 hours, let's run it for 1 hour or for 45 minutes. Let's just reduce that running time of the fans and the pumps and the chillers and the boilers and the cooling towers. Just reduce the running time, reduce the kilowatt hours, reduce the electricity bill. And that's where we sort of are right now. We're trying to start the building as late as possible to save the runtime of equipment. That's what we're doing. And, you know, in some countries, we're quite good at doing that. The problem obviously is that as we compress this pre-start time, as we compress it just to save runtime, we're actually making everything start together and run quite hard. So the chiller system starts up, it runs quite hard for a short amount of time. Rather than running for a long time, for 3 hours, running the chiller system harder for a short amount of time. That's what we're doing right now. So, and I'm proposing, and we'll explore this further through the video, that although it's ticking the box of lower runtime of equipment, it's creating peak demand issues. So let me jump on the screen here and I will show you an electricity bill. Right, so we'll roll through this. Let me just get rid of that my little face there. Obviously, we're not going to go into too much detail. You can go and see this in the membership if you want to go into it in detail. So this building for the month of March 2024, the electricity bill that the building owner paid from the retailer was $37,000. Let's look at what is made up from that. So obviously here is the month of March. These are the kilowatt hours. So this was the consumption of running equipment, fans, pumps, chillers, boilers, cooling towers. This is the running consumption for the month. And here's January, February, March consumption. So you'd have this in your energy management system, which we discussed last month in the membership. So over here we have the off-peak consumption and the peak consumption. So 17,000, 76,000 off-peak peak at about 7 cents per kilowatt hour comes to this number here. So in the month of March, we used about 94,000 kilowatt hours of electricity, and that cost about $7,000 on the bill. 7,000. Now 7,000 is not a massive number compared to 37,000, right? So 7,000 is our consumption costs, and then we have these like fixed charges. And for example, that 94,000 up there, it gets used over here, multiplied by different rates for these fixed charges. So for example, here we have green power, which is costing them $4,000, and there's a few other things. There's 1,000 here, there's another 1,000. Some big numbers in here. So there's a lot of money really associated to the fixed charges, but the consumption was only 7,000. Now here is where it starts to talk about peak demand. So this building, the maximum kVA demand, we don't talk about kilowatts, it's actually kVA. The highest actual metered demand this period was 1,128 kVA, recorded on the 12th of March 2024 at 7:30 a.m. Now how this works in Australia, I don't know how it works in other countries, but how we do it is the retailer picks the highest peak that you had in the year, just that one little thing, that on that day, at that time, something bad happened and we used a lot of peak power, and they charge you every month for the next 12 months on that highest peak, and they reset it. So you make one mistake with your peak demand management. We don't do any peak demand management, but I'm just saying, you get penalized for that for 12 months. So on this day, you can see over here, it was on the 12th of March was here. And you can see through the rest of March, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, this is actually a Tuesday. And actually, I just checked that a minute ago. The 11th of March was a public holiday, which is extremely relevant to this discussion. I'll just mention it now because I probably won't remember later on. But this public holiday was a hot day. This Monday was a hot day. So the building did not run on Monday. It also didn't run on Saturday and Sunday. So over Saturday and Sunday, probably quite warm weekend because it's summer. And then with this very hot day on the Monday, the whole fabric of the building, the concrete, the carpets, the ceilings, the walls, the building is warm. So on the Tuesday, we started up and, it would have been everything going, all the AHUs going hard, the chillers staging up all the way up, pumps running hard, and bang, peak demand hit here because of that one day. And now we're paying this money for 12 months. Even if it doesn't happen again next month, it doesn't matter. You are now locked into that tariff, that rate, and you're paying this amount for 12 months. If Monday wasn't a public holiday, I'm proposing that this number would be right down here somewhere. It wouldn't be there. It would be down here somewhere because this is the average. So the key with this slide, what I want to explain to you is the peak demand cost, the highest that happens in summer, you're paying that for the whole 12 months. It doesn't auto reset every month. You pay that for 12 months. And here's the costs. So here's the cost. So network rolling demand is what they call peak demand. And there's that number, 1128. So it's 1,128 kVA multiplied by $10 gives you 12,000. So on this electricity bill, the building owner is paying $12,000 for the peak demand costs. They're only paying $7,000 for the consumption costs. So it's a real significant number, the peak demand. We spend so much time thinking about how can we run equipment more energy efficiently, how can we slow pumps down, how can we slow fans down. We can spend so much time trying to reduce the consumption cost, the 6,000, and we aren't thinking at all about trying to manage peak demand better, which is a much higher cost. Now this particular bill, I don't know if this is with all retailers in Australia, but they've got this thing called summer demand incentive. You might not have it in the country where you live. How this works, and I had to call up a sustainability engineer because I didn't know how this worked before I did the course. What happens here is that every day through the month of summer, December, January, February, for example, in the afternoon between say 4 p.m. and 7 p.m., the retailer checks your peak demand. So every day through the month of March, they check your peak consumption every day in the afternoon between like 4 and 7 or something, and they pick the highest number and they penalize you on that number. So whereas the main peak demand, you get penalized for 12 months for one mistake, and then the summer demand incentive, which I think should be called summer demand penalty because they're not giving you a discount incentive, they're penalizing you. 544 kVA was the highest peak we had in this month in summer between 4 and 7. That was 4,000 for the month. So the peak demand costs are really 12,000 plus 4,000. So it's even worse than the 12,000. And this is kind of interesting because we don't exactly know when we're going to hit the peak here. We can guess actually, but this is kind of easy. You know, this happens somewhere between 4 and 7 p.m. So we should have an optimal stop. So if we have an optimal stop in summer from 4, which is not that, it's just quite close to the end of the day anyway, we could flatten this down also by $1,000 or whatever it is. All right. So I'm going to move off the invoice now, but I want you to understand here, the takeaway for this little discussion is that peak demand is it's a big dollar number in the electricity bill, much more than the consumption cost with this particular building, this particular retailer in this particular country. The first thing. The second thing is that when you have a peak event, they capture that high number and you pay the 12,000 for 12 months. Even though in winter, when our peak will be much lower because we're not running the chillers, you're still paying the 12,000 for the next 11 months because just that one mistake you made. So if we can have some peak demand management control strategy and the BMS says, whoa, hang on, it's a warm weekend, the plant's not running, it's a warm Monday, it's a public holiday, it's a 35 degrees Celsius day on Tuesday, we're definitely going to hit the peak. Let's get smart about it. Let's do something different. All right, let me show you something else quickly. So when I was like, with this peak demand, I've discussed peak demand like, hang on a sec. Hi, there's my face again. I've discussed peak demand in a lot of other types of training courses over the years, just like for half an hour. I just used to tell them about, in the electricity bill, there's a thing called peak demand. You get penalized for 12 months. Obviously, when I created the actual full-on course and the membership, I wanted to expand on that. That's why I went and got the electricity bill. And I went through all that. And then I thought, well, let me try and get data for a bunch of buildings to try and put some numbers behind this, some real numbers. So in this spreadsheet, which I will not go into detail here, there's 9 buildings in the spreadsheet. There's the 9th building. There's 9 buildings. This is a 58,000 square meter building. This is a large building, 26,000. It goes all the way down to 7,000. I want to get like a good split across a large building, medium-sized buildings, and small buildings, rather than just look at one big building. And then I got the data for 4 years, 2022, 2023, 2024, 2025. And I got the data of, in that year, what month, what day, what time did they exceed the peak demand? All right, so in 2022 at 6:45, we hit 1,133. Next year, 708, 1,128. So, and this is the one we've been looking at in the invoice. This is the invoice for this month. It's the 12th of March. This is the one. This is the actual invoice for that one. And then I have the outside air temperature at 9 a.m., the outside temperature at 3 p.m., the outside temperature the day before, and the outside temperature 3 p.m. the day before. Now, in that electricity bill, the day before, the Monday, was a public holiday. So the day before, on the public holiday, where the building did not run, it was a 35 degrees Celsius day. It was a very hot day on that Monday when we were at the beach with sunblock on, sun tanning, while the plant wasn't running. So Tuesday was going to be, it's kind of obvious. Like the actual Tuesday at 9 a.m. it was 22 degrees Celsius, at 21. It actually wasn't that hot. The actual Tuesday when we hit the peak, it wasn't actually that hot. It was all that damage from the weekend before and the Monday before that we tried to very hard cool down. So I got this data here, and then I just got the electricity costs, and I worked out, what they were paying per month, what they're paying per year, and then I worked out some, I'm not going to discuss this now, it's too complicated, but in the course we go through, I actually try to work out what are the potential savings we can make by having an active peak demand management strategy. So for this building 1, 60,000 square meters, if we were running peak demand management this year, 2025, we would have saved the building owner $36,000 of saving. And that's actually a conservative estimate, which I explain in the course. It probably would be more than that. I was very conservative in the savings discussion here. So across those 4 years, they would have saved $153,000 across 4 years. Now you can imagine this, right? If they're going to save $36,000 this year, what could you charge them for a peak demand management little optimization mini course is the first thought. And here's the big one. How much could you charge them for peak demand management maintenance every single year? I reckon you could charge them like $10,000 or $15,000 every year to maintain the peak demand management strategy. So rather than doing periodic preventive maintenance, we charge our customers, here's the amount of money to maintain the energy management system. Here's the amount of money to maintain the chiller management system. Here's the amount of money to maintain the peak demand management system. So asking your customer to pay you money to maintain systems that generate savings to them. Periodic preventive maintenance, the customer makes no money from that. Anyway, sort of like digressing slightly. So let's get back on track here, because we start off by talking about optimal start. Start the equipment as late as possible, reduce runtime. And now we've discussed this idea that peak demand management is a flippin' real thing that costs real money, like real money. We should be thinking about it. So it got me thinking about, okay, look, the first thing is optimal start and peak demand management are related. The two are related. You should be thinking about them together in your thought process. There is no point having an aggressive optimal start that reduces power consumption, running equipment, but we hit the peak. If our optimal start starts our equipment hard or hit the peak, that's a bad thing. We're reducing runtime, but our customer's paying more money actually in the electricity bill for the peak demand. So if you have optimal start, you should have peak demand management built into it together. Right. The next thing is that got me thinking. So okay, look. So what will we do? Maybe if you're forecasting. Okay, the forecasting is a bit more of a complicated discussion. Let's just step back a little bit. Say, for example, like the most simple thing would be this: when the plant starts up in the morning, if the outside air temperature is greater than a certain number, the optimal start goes into a peak demand start. So rather than starting for a short time, we would say, okay, look, it's going to be a hot day today this morning. Let's start the system 3 hours earlier. like 3 hours earlier, and let's stagger start the AHUs. So you've got, say, 20 AHUs. We bring them on like groups of 4. Bring 4 on, 4 on, 4 on, 4 on over, I don't know, half an hour or an hour. Just don't know, I'm making it up. So, and then the chiller system, when it starts up, the first thing that happens is it's only getting demand from 4 AHUs. So it starts up gently. Just gently starts up. There's not 20 AHUs running with cooling valves fully open. It's 1 AHU starting, sorry, it's 4 AHUs starting up, another 4, another 4, another 4. So that chiller system starts up gently. Comes on 50 minutes later, the next 4 come on a bit more. It's gently picking up the load. That's a very basic thing to do. We could also limit the AHU fan speeds to 80% or 70% or 60%, an adjustable, tunable parameter. So when the AHUs start up, the supply and return fans, we limit their speeds. They start up slowly. And for the chiller system, we could limit the number of chillers that are allowed to run in a peak demand startup. So rather than having like 5 chillers running, only 1 or 2 are permitted to run. So maybe we disable the low load chiller and we have 1 high capacity chiller available. Only 1, not 3 high capacity chillers. 1 chiller starts up, and we can also limit the capacity of the chiller to 80% capacity through the high level interface. So the point I'm making here is to protect the peak, to flatten that peak off for today and save money for 12 months, we start the chiller system up or the whole building up a longer period gently. I think that's a great idea. And that then got me thinking, and this is like the part of this video, the title of this video is that, do we have optimal start wrong? Then I was thinking about, well, hang on a second, like, why don't we just always start the chiller system up or the building up gently? Why don't we just always do it? Because I don't know if running the whole building very hard, fans running hard, supply fans, return fans, cooling valves open, chillers pumps, cooling towers, I don't know if running the building very hard for 1 hour is better or worse than running the whole building for 2 hours gently. More time, less kilowatts. And the exciting part of it is that, not exciting, the disappointing part about it is that we should know this. We are the building management system specialists. We are the control system specialists. This is what, like, we are the specialists, and we don't know this. We should know by now, for this building of this age, this type of mechanical equipment, this efficiency rate, we should just know that this building works better like this or like this. So service departments, these are the sort of things we should be doing for our customers, analyzing their buildings, working these things out. We should know that if you're a service technician, and I'm going to exaggerate my point here, but if you're a service technician and it's Saturday and you're sitting on the beach sun tanning, you're like, oh my gosh, my phone says that, it's a hot day, Saturday, Sunday, and my phone is saying that on Monday it's also going to be a hot day. You should be thinking, shit, we're definitely going to have a peak demand event on Monday. Like, you should know that. Or you should be looking at the forecast thinking, hang on Thursday it's going to be a very hot day. Wednesday is quite a hot day. This building has peak events in these sort of conditions. We should know these sort of things. We should be offering our customers like control strategy, optimization, mini projects to implement peak demand. Every single building should have a peak demand management control strategy. It should be interlinked with optimal start. We should make money by offering this, and we should make money by maintaining these things. We are periodic preventative maintenance rock stars, but we are not great at the stuff that actually generates value for the money that our customers are paying us. For those of you that are on the membership, I always do this. Give me 1 second to go to my wall quickly. Around 80% of buildings in cities today will exist in 2050. Around 80% of buildings in cities today will exist in 2050. So if you jumped in a time machine and you went forward to 2050 and you walked around the city where you live, 80% of the buildings you see, they're already here now. We have them now. So we should be focusing on the existing buildings market. We're not going to build that many new construction buildings between now and 2050. But these existing buildings, the existing building stock from the 1970s, 80s, 90s to 2050, this is where we should be focusing on. We should be focusing on existing buildings and peak demand management and optimal start in this discussion. Like I'm telling you now, just being a specialist in peak demand management, just look at the electricity bill today and some history of when buildings hit their peaks in the morning. A company could build an entire business around this. You could just be a specialist in doing this because every building really needs needs peak demand management, and no buildings have it. Now in the membership, it goes deeper into like coordination with the retailers, coordination with the grid. There's also other things we discuss, but this whole peak demand management thing, it is like money that BMS companies are leaving on the table and building owners are leaving on the table because they can save money. This is a reasonably easy sell in my opinion. Like, here's the electricity bill, that's what you're paying, that's when you hit the peak, there's the history, there's the data of it, we can flatten that off. It's an easy thing that there's real numbers you can show in a case study. I was even thinking about yesterday, like, even as a BMS consultant, like, I could build a consulting product here. I bet you I could sell to building owners, pay me $20,000. I'll put together a peak demand management, optimal start and optimal stop specification. I'll issue the BMS company. They'll give me a quote. I'll review their design. We'll have meetings, review the technical submissions, do witnessing, commissioning, tuning, and a fee to support for the first 12 months afterwards, whatever it is. If I wanted to, I bet you I could have, this could be a full-time business because every single building needs peak demand management. Now, just a quick thing. In that spreadsheet, as you go down the sheet, there's less potential for savings in smaller buildings. So smaller buildings save less money, like, 7,000, 1,000, 1,000 around. Oh, you can't see it. My face is in the way. There's not a lot of savings really for smaller buildings. But what I think should happen is you would just pick out your 5 biggest buildings in your maintenance portfolio and do the peak demand management. Again, like this is a YouTube video, but like in the course we go through, the difference between construction and construction projects and BMS upgrade and peak demand. So there's a whole discussion around that too. Anyway, let's wrap it up there because I'm dawdling a bit now and getting distracted. But join the BMS Professional Development Membership, pay a low monthly fee, cancel anytime, go deep into peak demand management, optimal start, and build up a revenue stream for your business or yourself. Thank you for watching, and I will see you in the next one.